Hello everyone, welcome to Chapter 3, Mechanical Properties of Materials. Today, we're going to explore how different materials behave when we pull them, push them, heat them, or apply different types of forces. Let's begin. Before we test materials, we need to understand how they are loaded. There are two types of loading, which static load and dynamics load. Static load is a constant or slowly changing loads, like the weight of a building or bridge. While dynamic load is a loads that change suddenly or create vibrations. Dynamic loads include periodic loads like rotating machines, random loads such as earthquakes, and transient loads, which is short impulse loads like trucks passing over a bridge. Different loads can affect materials differently, so testing is important. One of the most important tests is the tension and compression test. This test tells us how strong a material is. We prepare a standard specimen, measure its original length and area, and place it in the machine. The machine slowly pulls or pushes the specimen. As the load increases, we record the applied force, the change in length. This helps us understand how the material behaves under normal stress. When we plot stress against strain, we get the stress-strain diagram. The nominal stress is calculated from the applied load and the original cross-sectional area of the specimen using the formula where axial load divide with initial cross-sectional area. Similarly, the nominal strain is determined either directly from strain gauge measurements or computed as the ratio of deformation to the original length, where the change in length is divided with original gauge length. This graph is like a fingerprint. It tells us almost everything about the material's behavior. Let's look at the different stages. So for elastic region, the stress is proportional to the strain and the material is linear elastic. Moreover, the proportional limit is the point where the stress-strain line stops being straight. After this point, the curve begins to bend. This behavior continues until the elastic limit is reached. If the load is removed at this point, the specimen returns to its original shape. For yielding part, when stress goes above the elastic limit, the material deforms permanently. This is called yielding. Yield stress is the stress at which yielding begins. After this point, the material deforms plastically and continues to strain without increasing load. This is known as perfectly plastic behavior. Now we move on to strain hardening region. After yielding ends, the specimen can support more load, causing the stress-strain curve to rise steadily until it reaches maximum stress, known as ultimate stress. Up to the ultimate stress, as the specimen elongates, its cross-sectional area will decrease uniformly over the specimen's entire gauge length. Lastly, necking region. After the ultimate stress is reached, a small region of the specimen's cross-section begins to thin, forming a constriction called necking as it continues to elongate. The stress-strain diagram tends to curve downward until the specimen breaks at the fracture stress. The image shows a tensile test specimen exhibiting necking, a localized reduction in cross-sectional area that occurs in ductile materials under uniaxial tension, typically just before fracture. While this image illustrates the final stage of failure in a ductile material, where the specimen has fractured after significant plastic deformation and necking, resulting in a characteristic cup and cone fracture surface. Now I'm going to talk about modulus of elasticity in elastic region. E represents the constant of proportionality, also called the modulus of elasticity or Young's modulus, and has stress units, PA, MPa, or GPa. There are two types of modulus, which are modulus of resilience and modulus of toughness. When stress reaches proportional limit, strain energy density is called modulus of resilience. A material's resilience represents its ability to absorb energy without any permanent damage. For modulus of toughness, graph indicates the strain energy density of material before it fractures. Shaded area under stress-strain diagram is the modulus of toughness. And last one for this topic, I'm going to show you shear stress-strain diagram, including its important formula. This is shear stress strain diagram, including two formula. G is shear modulus of elasticity or modulus of rigidity. So that's all for today. Thank you for watching, and I hope you found this presentation helpful.